so far seen how to measure flux density in a core using ballistic galvanometer. And so far I have said that the derivation that we did is an approximate one. It's not very accurate. Can you guess why did I say so? The reason is, here say in this line I am estimating the current in the secondary or the search coil by dividing the EMF induced with the resistance of the search coil. But what about the inductance of the search coil? Is there no inductance? Definitely there is, and because after all this is a coil. So, a coil with a magnetic core must have some inductance. Can we neglect it? We can neglect it possibly if the inductance is low, but that will also mean the EMF induced in the secondary will also be low, because when will we have low inductance? Maybe if the number of turns is low, or maybe if the permeability of the core is low, so on. And in either of these cases, that will mean the EMF induced in the secondary is also low. So, we have to also ignore the EMF, but then we cannot do this measurement at all. Secondly, okay, is this current that is flowing, is it DC, so that we can neglect the inductance? It is not necessarily DC, because the EMF generated is not necessarily DC, because the rate of change of this current or rate of change of this flux, they are not necessarily constant. So, this derivation is an approximate one. Okay. So, yeah, maybe if this rate of change of current is constant, if the current is changing like this, initially constant and then it goes down to 0 with a constant slope, okay, then flux is also going down with this constant slope, then the EMF is constant, and possibly then we can follow this type of analysis. So, let us do a more precise calculation, which is also simple. So, let me first write that EMF induced, which can be a function of time, okay, is always ddt of psi t, where psi is the flux linkage of the secondary coil. Okay. So, and the psi, the value of psi is equal to, okay, let me write it again. So, the value of psi is phi multiplied by N2. N2 is the number of turns of the secondary or search coil, and phi, this can also be a function of time. Okay. And then this should now be equal to the resistance multiplied by IT, where I is the current in secondary coil, okay, and resistance is the resistance of the secondary coil circuit, plus L ddt of IT. Okay. So, let me write where IT is secondary current. So, this is a function of time, okay, and R is secondary resistance, L is secondary coil inductance, okay, and yeah, E is of course also E is EMF induced in secondary. Let me write it this way, or okay. Psi is of course flux linkage of secondary. Okay, I guess I have written everything. Okay. N2 is of course secondary number of turns. Now, okay, so now this phi t, I can write this as this is equal to B, also function of time, multiplied by A. Okay. So therefore, from this we can write that ddt of this thing, in place of phi I write Bt A into, okay, and this is equal to R IT plus L ddt of IT. Now let me integrate this equation both on the left hand side and right hand side over time. So let me do it this way: ddt of Bt A N2 multiplied by dt, and over the time say call it T0 to T1, where T0 is the time when the current started to change and T1 is the time when all the changes are over. Okay. So this is the time when things started to change, and this is the time when, I mean, this is long enough, this time is long enough so that all changes are complete. Okay. So now on the right hand side I write R is a constant, I put it outside, IT dt T0 to T1 plus, here I will have L constant, integration of ddt of I dt T0 to T1. Now this now what is this? ddt of Bt dt. If we integrate, so this part, this is the rate of change of B, and this is multiplied with dt and integrated. So that means after integration this will give total change in B. Okay. So this left hand side is after integration will give total change in B, and this is a constant. An2 is a constant. So this I can take outside An2, and this is multiplied by the total change of flux density, total change of B from T0 to T1, from time T0 to T1. This is the left hand side, and right hand side will now be equal to, now R T0 to T1 IT dt plus, what is this term? L is a constant, and this is rate of change of current multiplied by time and integrated. So this will be total change. So this will be total change in current, in secondary current. Now let's keep this as it is. Or okay, so let me put the val. So this I write as R, okay, and what is this? Current integrated over time. Current integrated over time is charge. So this will be charge flown within this time t0 to t1 plus what is this? L is a constant, and what is the total change in IT? So this is equal to final value of IT minus initial value of IT, or I at t1 minus I at t0. Now this is equal to 0. Why? Because initially secondary current was 0, finally also secondary current is 0, because secondary current flows only during the time when the primary current is changing or when the flux is changing. Before that, that means before I open this switch, the secondary current was 0, and long after all the things got stabilized, the secondary current is again 0. So this term therefore is 0. So this I write as 0. So right hand side is R times charge flown, and what is the left hand side? Left hand side is AN2 multiplied by total change of flux density. Okay, so let me come here. Okay, so the left hand side is AN2 multiplied by total change of B. Now what is total change of B? This will be again final B minus initial B. Final B will be 0 and initial B is whatever that value is. This is the unknown initial B. Okay, this is final B, which is 0 if I am using this circuit, so that the current is 0 finally, so final flux density is 0. Okay, so then I have this is left hand side, and right hand side is R times charge flown. Okay, equal to R, let's write it Q. So then I have from this Q is equal to the magnitude of Q, okay, is equal to B A N2 divided by R, and that's what we got here as well. Okay, so okay, it's written here. So Q is B A N2 by R. So the approximate derivation gives the same result as this rigorous derivation. But the approximate derivation we did initially because I thought that is maybe easier to remember, easier to see the things fast. I mean realize what is happening. Okay, but this is a more rigorous derivation and it gives the same result. Okay, and yeah, and let me also write that this is for the case when final primary current is 0. Okay, we can have a factor 2 if the final primary current is reversed. Okay, if that means this circuit, if we use this circuit, then the final primary current is reversed, so total change in flux density will be doubled. So we will have a factor of 2 here, okay, at this point, if we use the other circuit. Okay, so that's it about ballistic galvanometer based measurement of flux density. Now let us move to our second topic in this chapter, which is Hall effect sensor. This is also a small and easy topic, I believe. Okay. Let's first understand what is Hall effect. Okay. Suppose I have a block of some material which is called Hall material, and what I do is I have this block in a magnetic field, and say the magnetic field is in this direction. So the magnetic field is okay. Let's take magnetic fields vertical like this. Okay, and they continue through this block, although I am not drawing through the block, but they continue. These are continuous flux lines. These are magnetic flux. Okay, so magnetic flux lines, they can be upwards or downwards. Either is fine for now. Okay, and then what I do, I take, say, I pass some current through this block from one side to the other side. So let me connect a metallic plate on this side, similarly on this side. Okay, and I pass some current from one plate to other. Call this current I. So the current is entering through this side and is leaving through the other side. Now, when this current flows from one side to the other, okay, so suppose I also have a closed circuit here, so that current can flow, okay, like this. And if you want, you can put an ammeter to measure this current. So this is the arrangement. Okay, now charge is flowing from left to right through this block, and that means also the electrons are flowing from right to left. Okay, so now when this charged particles, say electrons, if they are flowing through a magnetic field, they will experience some force. What kind of a force? That force will be perpendicular to both the direction of this magnetic field and the velocity of this charged particles. Okay, so if this are the electrons, so electrons are normally flowing like this, but this magnetic field will cause a force on these electrons, which, and the direction of that force will be perpendicular to both the field and the velocity. Okay, so we can find this by using left hand rule. Okay, so for example, let's assume if this is the direction of the field H upwards, and if we had positive charge, plus q flowing from, say, left to right, because the current is from left to right, okay, then what will be the force on this positive charge? So let's find that out. So the direction of current is left to right, field is upwards, so I'm applying left hand rule, field is upwards, direction of current is this, left to right, direction of positive charge, and my thumb is pointing towards me, I mean outwards, upwards. Okay, so this will be the force on the positive charge. Now if you think in terms of the electrons, then their charge is negative, so the force should be in the opposite direction, but their velocity is also opposite. So that means two opposite things will cancel each other and the force will remain still in this direction. Okay, so force, so this is the direction of force. So therefore what will happen? Okay, so the electrons were normally flowing like this. Due to this force, they will come towards this side. Okay, so the electrons will have a force which will cause them to deviate in this direction. Okay, and then, so if electrons are flowing in this direction, okay, it's possible that there will be some accumulation of electrons on this side. Okay, so because of this force, so there will be some accumulated or accumulated electrons on this side, and okay, there will be a situation when these accumulated electrons will repel the flowing electrons, and thereby equilibrium will be re-established. Magnetic force, this is the magnetic force, is in this direction, and this accumulated electron will give a force in the opposite direction. So we can have a equilibrium established. But in this process, what will happen? There is some stored charge on this side and some less charge on the other side. So now if we measure the potential difference between this side and the other side, which is behind, which we cannot see, then we will see there is a potential difference, because there is an accumulation of electrons due to this magnetic force. Okay, so now what we can do, we can actually say put a metallic plate here on this side, okay, and similarly another plate on that side, okay. So this is a plate, that is another plate, and now what we are going to do, we are going to measure the potential difference between these two plates. take a voltmeter. So we will see some voltage appearing here, and this phenomena is called Hall effect. So what is the phenomena? The phenomena is that we have a magnetic field. In that field we have some current flown, and if when this current is flowing, the magnetic field will give some force on these charge carriers, and therefore they will get diverted on one side, causing a potential difference between these two plates. Okay, these two plates should not touch these orange plates, of course. Then there can be some sorts, there can be some problems. Okay, so we will have some potential difference between these two plates. This is called Hall effect. And this voltage, what does this depend on? This voltage depends on, of course, the velocity of these electrons, which in turn depend on the amount of current. More the velocity, that means of course the current is more, and it is also proportional to the field intensity, magnetic field intensity. Okay, magnetic field intensity H. Particularly in the direction perpendicular to the to both this, to the current and this where we are measuring this voltage. So the component of H along, say, y axis. Okay, so this is, say, this is y axis. Okay, magnetic field intensity H along y axis. So this voltage depends on these two factors. Now if we know okay, so okay, before that, so that means we can write that this voltage V is equal to some constant times this I and H. You can call it Hy in the direction along y axis. Okay, now if we say no this I, because this is the current we are passing, this is in our control, so I is known. Therefore this quantity H can be estimated from these two values V and I. And by this we can measure the component of H or Hy in this particular direction. So this is an phenomena called Hall effect, with which we can measure magnetic field intensity, and then this measurement is direction sensitive. Okay, so if I put this block in different orientations, the voltage generated here will depend solely on the component of H in this direction, not on any other H. Okay, so this is what Hall effect sensors are. Thank you.